Hey, all right. I'm gonna write up a little warm up exercise. This one's like really straightforward, so um, probably only takes about, I don't know, 5 minutes or so, uh, and then we'll get into some more, bit more sophisticated problems. Let's see. So take for granted that, let's see, sine of x, cosine of x, and e to the x are continuous for all x, and log of x, x to the p are continuous for all x greater than 0 and for all p. Then use the theorems of section, what is it, 17, to show the following are continuous. So we'll do sine squared of x plus cosine to the 6th of x to the pi power, 2 to the x squared, and 1 over x sine of 1 over x. Yeah. And also, just in case it's not clear, when I write log of x, I don't know, the book, I guess they do log base e or something, but whenever I write log of x, that means log base e, okay? Otherwise known as like ln or whatever. But I just call it log of x because pretty much almost never like interested in any other bases for the logarithm, I guess. But yeah, anyway, so this should be pretty quick. Yeah, let's go ahead and like say we'll resume at 5, I don't know, 13. All right. Okay. So let's just sort of go over this pretty quick. Okay, for the first one, right. So first, what we can say is that, what was it? The theorem about adding and multiplying, I think that's 17.4, right? Okay. So, so for this one, we'll say 17.4 tells us, right, that sine squared of x is continuous and cosine to the sixth of x. You can use like several applications, right, to get cosine to the sixth of x, that's continuous. And then using 17.4 again, this is like 17.42, I guess, right? And then 17.41 tells us that the sum is continuous, right? Plus cosine to the sixth x. And then the domain of this overall function is actually, so this is continuous. And then the domain of the overall function should just be wherever sine and cosine, or wherever. Oh, I guess this is always positive, so it doesn't matter, right? So yeah, the domain of the function is actually still like all x. And then so then 17.5 tells us that the overall function is continuous. So overall f is continuous. Okay. Any questions about that?
Yes, I have a question. So like here we just said to the power of pi.
Yeah.
And this is constant because pi is a constant.
Yeah, pi is a constant. So
And so that's why to the power, that's like the composition.
yeah. So it's like, this is the composition. Okay. If you write, so if we call this like h or something is the overall function. And then if we say like g is like g of x, g of x is like x to the pi for x greater than 0, and then like f of x is sine squared x plus cosine to the sixth x for all x in R, then h is g compose f.
Yeah.
Okay.
I think my question is probably like if we say like x to the power of 2 or to the power of 3, then we know that like they're just like multiply for several times, right? For 2 or 3 times. But like pi,
Oh, sure. Yeah. You could use the product. I guess we could actually use. We don't have to use 17.4 here either. So you could go either way basically, since we know x to the p. Actually, it's kind of annoying to do it with x to the p for this one, because this is for x greater than 0, and sine is not always greater than 0. So for integer powers, we want to stick to using, at least in the context of this specific problem, if we're dealing like with these integer powers of sine and cosine, we want to use 17.4 part 2. And then for the raising to the pi, we have to use 17.5 because pi is a irrational number. Yeah. Okay. So for the next one, the way this problem is stated in the book, they also give us that 2 to the x is continuous, but I thought it was like a little bit more interesting if you have to like sort of show that too. So first you can say, first we argue that, well, so x squared is continuous. That much is clear by, let's say, well, okay. I'm just going to say 17.4 because we don't want to restrict ourselves to x greater than 0. I mean, I guess you could actually say like, okay, this is continuous for x. Actually, no. I'm just gonna, okay. So maybe it's like an unstated assumption here that x is continuous for all x. Okay. Yeah, because this is like really trivial to prove. So we can say x squared is continuous for all x by 17.4. And then we'll say also like 2 to the x is continuous for all x because so 2 to the x equals e to the log of 2 times x, right? And log of 2 x is continuous by, you know, what's it, 17.3, right? So by 17.5, e to the log of 2 x is continuous, right? So that means 2 to the x is continuous, and then you can use 17.5 one more time to get that 2 to the x squared is continuous. I guess actually you can even do it sort of more directly just by saying you can just say like log of 2 times x squared. Yeah. Then like log of 2 times x squared is continuous by, that's the 17.3 again. And then 17.5 just directly tells us that e to the log of 2 x squared is continuous. So 2 to the x squared is continuous. Okay? Yeah, that's actually a bit simpler. All right, any questions about that? Okay. Yeah, and then this one is like, so obviously the domain of f is just, you know, the set of x not equal to 0. So, you know, here, so in the domain of f, we know, you know, 1 over x is continuous. And, you know, sine is continuous everywhere. So, you know, 17.5 tells us that sine of 1 over x is continuous, you know, for x not equal to 0. And then 1 over x sine of 1 over x. Oh, yeah. Ran out of space. Okay, whatever. If we call this f, you know, so f is continuous. That's by one more application of 17.4, right? So we just multiply sine of 1 over x by 1 over x, and we'll get a continuous function that way. Okay, so hopefully that's not too bad. It's just kind of like basically breaking down how these functions are built up from these like small pieces, you know, looking at like, you know, what order you do these different steps in, and then just applying the corresponding theorems. So it really shouldn't be too difficult, but you can kind of see like how much stuff you can get just by using these theorems and a couple basic ingredients, you know. Okay, so let's see. Actually, before we move into another problem, I figure I'll just like open it up for any questions you might have about, you know, anything up to this point. Any questions?
Yeah, I had a question about, so proving um, continuity or discontinuity. So like, what exactly like can we, and like what do we have to let, like you remember how like there was that like game with the devil or whatever? Like I'm
Yeah, right. Yeah.
yeah.
Uh-huh. Yeah, it's like the same. If you want to sort of proceed directly from the definition, it's basically the exact same structure, but instead of capital N, you pick delta, right? So it'd be like, right. So if you'd say, here's epsilon, right? I guess first you'd say, I mean, you have to fix, x naught, I guess, right? Then you'd say, well, here's delta, right? And then he'd say, okay, here's x, right? At a point x for which, so this is x such that, x is in the domain of f, and this is less than delta. And then the question is f of x minus f of x naught less than epsilon, right? So in a proof, you'd say let epsilon be greater than 0, and then stuff about picking delta, then you'd say like, no, let x be in the domain of f such that x minus x naught is less than delta. Then, show that f of x minus f of x naught is less than epsilon, right? That's kind of, at least ideally, or sort of like just very, very formally, this is how the proof would be structured, I guess. But of course, like in practice, it's possible to like mess with this a little bit because, a lot of the time the way things end up shaking out is that like in the process of describing how you pick delta, you kind of prove like this part as you go, right? Because it's kind of like, well, okay, here's the thought process behind why we pick delta the way we do. And then when you lay all of that stuff out, it kind of makes it obvious that just by kind of like going backwards through the chain of logic you followed to get to delta, you'll arrive at the fact that like this is true for the choice of delta that you made, right? So that's like a valid thing to write down, like if you're trying to like write a proof or something. And honestly, it's almost preferable to do it that way, because like if you really want to proceed strictly kind of in this forward direction like this, then what you have to do is you have to sort of do this like side scratch work where you figure out what delta is, and then in the actual proof you write down, you kind of like pull delta out of thin air, right? And then like all this like magical stuff works out where like this ends up being true for your choice of delta because you did all the scratch work to figure out what delta was, right? But it's sort of like more natural for the reader to see the thought process of choosing delta beforehand, like and then it'll be obvious that the choice of delta you arrive at will be valid, right? So I don't know. I actually think in practice it's almost better to do it that way. The reason early on I kind of emphasize like the forward direction structure of the proof is just because like in principle that's actually the direction that the logic itself flows, right? Like you can only really get comfortable with writing the proofs where you kind of like go through this logic backwards and then find delta if you understand that what you're writing down sort of implies that you could write the proof the other way where all of the logic goes forwards, I guess, right? But anyway, I don't know, whatever. It doesn't, at this point, like it's not a big deal. You can sort of do whatever you want. But this is ultimately like, if you come up with a valid proof, you should be able to like structure it this way somehow. Yeah.
Okay, yeah, thanks.
Yeah, this never changes, of course. And neither does this. Okay. Other questions? Okay. Let's see. Yeah. So let's see. Okay. Let's do. Let's actually do. There's a problem that's kind of like using the epsilon delta property, like demonstrating the epsilon delta property. Okay. So prove. So okay. Prove g of x is x cubed is continuous everywhere by showing it has the epsilon delta property at any point x naught in R. So x naught is kind of this like arbitrary but fixed point. And you want to show that G has the epsilon delta property at x naught. And so I'll give you some hints here because the algebra is like a little bit messy, but I think with the hints, it shouldn't be that bad. If you kind of just replicate what we did in the example with like 2x squared plus 1. So here's a hint. So the book kind of gives a hint, and I'll actually elaborate on the hint a little bit. So so x cubed minus x naught cubed is equal to x minus x naught, and then x squared plus x naught x plus x naught squared, right? So here's the goal, right? Remember, so we want to kind of like bound the absolute value of this above by like in terms of absolute value of x naught and delta. So for this, it might be useful to recall that if absolute value of x minus x naught is less than delta, then absolute value of x itself is less than or equal to absolute value of x naught plus delta. Okay, and then pick some constant upper bound for delta. Okay, so like you could pick 1 as a constant upper bound if you want, right? And then you'll get some constant. You'll basically end up with a constant upper bound for this part, okay? And then you just have to make delta be less than like the minimum of the constant you pick and epsilon over this, right? So yeah, I'll make a little chat room for you guys to talk if you want. And yeah, let's take like 10 minutes. So here, hold on. Yeah, all right. So let's see. Let me erase this. So let's just kind of go through the process I described here. So what I was saying is, so we want to bound this, the absolute value of this part above, right, by something in terms of x naught and delta. So let's see. So the first thing to do is just use the triangle inequality. So this is going to be less than or equal to x squared plus x naught x plus x naught squared, right? And then what I was saying is, in the end, right, like in sort of in the context of like the true proof or whatever, this quantity is going to end up being bounded by absolute value of x naught plus delta, right? So this is going to be less than or equal to absolute value of x naught plus delta, and then we have an x naught, and then we have another absolute value of x naught plus delta. Oops. And then we have just x naught squared. Okay. So this is, if you just expand this, you'll get, you know, x naught squared, all right, plus 2 delta x naught plus delta squared, right? And then we have another x naught squared plus x naught delta plus x naught squared. So all told, that's 3x naught squared plus 3 delta x naught plus delta squared. Okay. So if we make delta less than 1, then this is less than just 3x naught squared plus 3x naught plus 1, right? So then if we just pick, so I'm just going to write it up here. So pick delta less than the minimum of 1 and then like epsilon over this stuff. So 3x naught squared plus 3x naught plus 1, right? Then that should actually like suffice. I mean, that should work. You know, you should be able to build a valid proof with that choice of delta. Okay. So any questions about this? Do you guys see like how the proof proceeds? Like after you pick delta this way, right? Then what ends up happening is if you take, you know, absolute value of x cubed minus x naught cubed, then that's equal to the absolute value of x minus x naught times the absolute value of this thing. And then we bounded this above by, you know, I mean, the absolute value of this thing, we just bounded that above by 3x naught squared plus 3x naught plus 1. And then we know delta is less than that. So, you know, so this is like less than delta, and then this is less than like epsilon over this thing, and delta is less than this thing. So overall, it's less than epsilon. Okay. So here, let's see. Okay, let's try this one. So actually, I'm just going to kind of make this up. So let's say f of x is x squared for x rational and 0 for x irrational, right? So let's say for real x that are not rational, right? Where is f continuous or discontinuous? Prove your answer. Okay. And you can use either, you can use like, either definition if you want. So the limit one or the epsilon delta one, whatever you want, whichever one you prefer, you can use. Okay. So let's just take another like 7 minutes or something. It shouldn't be like super long, hopefully. All right, so I'll let you guys go back in the little room. Okay, so actually, I realized like while you guys were doing this that it would have been um, a little bit more interesting to make this be like X or something here, but I don't know, whatever. All right, so here's how I would do this. I would probably say, oh, well, okay, first of all, let's kind of like think about what it looks like, right? So we have like a parabola, and this is where like all the points where X is in Q. And then this is just where X is not in Q, right? So you'd think like any place, if you kind of zoom in at any point on the x-axis maybe, where X is not 0, right? If you just kind of look really close to any point, what you'll see is that the value of the function is just jumping back and forth between two totally different numbers, like infinitely many times in any interval that you look at, basically, right? And no matter how close to 0 you are, if X itself, if X naught, I guess, let's say this is like X naught, right? Or this is X naught or whatever. If X naught is not 0, then by zooming in close enough, you can kind of separate the parabola from the x-axis, right? So there'll be like this non-zero distance between them, and then F will just be jumping back and forth between those two values, basically. So we should expect F to be discontinuous at like every point on the x-axis except X equals 0, okay? So F is continuous at X equals 0 and nowhere else. And the reason it's continuous at X equals 0 is just because the two graphs here coincide at that point. So it's sort of like if you imagine, making a sequence approach this point on the x-axis and then looking at what the values of the function are doing, some of them are just staying at 0, and then the other ones are just approaching 0 from like along this parabola, right? So in either, like, no matter which points you pick, like no matter which graph you pick, the points are going to end up approaching 0 anyway. So it should be continuous there. So here's like a sketch of a proof, sort of a formal proof, right? So let's see, for let's say for X not equal to 0, or let's say, I don't know, call it X naught, I guess. Let's see. Then pick xn converging to x naught such that xn is in Q for all n, right? Then f of xn approaches, this is just xn squared. That approaches x naught squared, which is not equal to 0, right? On the other hand, pick xn, converging to x naught such that xn is not in Q for all n, right? Then, and this, when I say this, I mean like every single xn is an irrational number, right? Then f of xn equals 0, so f of xn converges to 0, right? So that's, we got two different limits here, right? So there's no way that, well, yeah. One of these two things is the value of f, and one of them isn't. But either way, whenever you can find two sequences in the domain approaching the same point, but have different limits for the values of f, then that automatically means f is not continuous there, right? So that shows that f is not continuous for non-zero values of x naught. And then I'm just going to like go back over this.
I had a question.
Oh, yeah, sure.
Yeah, so how is this different than the lecture question where like it's like similarly discontinuous or similarly like jumping back and forth, but it is.
The lecture question, if I recall, was about a function whose domain was the natural numbers, right?
Right.
So in that case, we had like f from here to the real numbers. And in that case, f just wasn't defined. So f wasn't defined for x not in n, right? So this function f is defined for every value of x, right? So the thing about this case here, when the domain of f is just the natural numbers, then like so like I said, when when I was sort of solving the lecture question, the only sequences in the domain of f that converge to a given x naught are those which are eventually constant, right? And that's just not the case here, because you can have sequences that just approach a given point, very slowly and kind of incrementally get closer and closer to that point, and they get just like arbitrarily close to whatever point you're looking at, right? So the fact that we can choose these sequences, right, the way we do here, this is like completely, this is necessary, and it's not something that we can do in this case, right? Like you can't take a sequence, I mean, yeah, like the only sequences approaching a given natural number, the only sequences of natural numbers that approach a given natural number are just eventually constant sequences. Does that make sense?
Yeah, I think so.
Yeah, so this function isn't really like jumping around.
Right.
Because see here, it's like when I say it's jumping around, what I mean is that like no matter how small of an interval you look at, right, it'll have values between two different places. It'll jump between two different values, even in a tiny, like sort of arbitrarily small interval, right? But here it's like the points are all spaced out from each other, and there's just like no values of f in between them to even really, allow us to assess like discontinuity or anything like that. Like the fact that all the points are just totally isolated sort of just automatically means f is continuous, I guess. Yeah. This one is just like a weird technical thing. Most of the time that we're actually interested in questions of like continuity or discontinuity are when the domain itself is like a continuous, like a set that like doesn't just consist of like isolated points, basically, right? So here the domain is like the entire real line. So it's this like filled in kind of continuum of points. And that's what actually makes the question of continuity interesting, I guess.
So like what if we change 0 into x and then we make when x belongs to an irrational number, fx equals to x? Is the function still discontinuous?
Right. So if x naught is 0,
yeah, that is still like different isolated points, right? Is it?
Well, so if x naught is 0 in this case, right, then when we pick a sequence converging to x naught that are all rational points, then f of xn converges to x naught squared, but x naught squared is just 0 in this case, right? And then if you pick a sequence converging to x naught such that xn is not rational, then it still converges to 0. So the two limits are the same in that situation. Right? And actually, in this case, that's not actually enough. Technically, like that's not quite enough, according to the definition, to prove that it's continuous there. What we really should do is let xn be an arbitrary sequence of real numbers converging to 0, right? So we would say like let xn be sequence converging to 0, right? Because x naught is 0. So then, of course, xn squared converges to 0. So pick, you know, capital N such that xn squared is less than epsilon, or like if you, you know, let epsilon greater than 0. We can pick a capital N such that this is true, right?
Yeah.
Then for n greater than capital N, either f of xn equals 0, in which case absolute value of f of xn minus f of x naught is 0, or f of xn equals xn squared, in which case absolute value of f of xn minus f of x naught equals xn squared, which is less than epsilon, right?
Mhm.
So in either case, man, I always do this. Let's see, right? I'll just move up here and I'll erase this. So in either case, f of xn minus f of x naught was less than epsilon for n greater than n. So f of xn converges to f of x naught, showing f is continuous at x naught equals 0, right? So we just showed that an arbitrary sequence in the domain that converges to 0, you know, for any such sequence, we can show that f of xn also converges to 0, which is supposed to be the value of f at that point, right? So so that shows that f is continuous at x equals 0, and f is discontinuous at every other point, like we said before, because you can find two sequences approaching x naught. For any x naught not equal to 0, you can just find two sequences approaching x naught where you get different limits for f of xn.
Oh, okay.
Yep.
Got it. Yep. Thank you.
All right. Any other questions about this? All right. Well, okay. So I'll see you guys tomorrow then.
Thank you so much. See you tomorrow.
Bye-bye.
Bye.
Thanks.